Leibniz theorem. We find the successive differentiation. This theorem is very helpful. Okay, so suppose y is a function of x, which is the product of two functions u and v. U is function of x and v is also function of x. So Leibniz theorem says that nth derivative of y is nothing but u n v plus nc1 u n minus of 1. See, this is the nth derivative. Next will become n minus of 1 derivative, 1th derivative, and v, for v this is the first derivative. This is only v. This is the first derivative of v. Then in the next term this will give you the second derivative of v. So nc2 u n minus of 2. So for this nth derivative, then n minus of 1, then n minus of 2. For v, what is happening? It is increasing by 1. For u, it is decreasing by 1. The derivative. Okay, so v2 plus so on. It will go like that, and nth term will be nc n v n. Okay, this is for the Leibniz theorem. So let us take one example, then you will understand it better. And we have to prove that 1 minus. So let us prove it. So here you see this is n plus of 2th derivative. So this is not the nth derivative, n plus of 2th derivative. So what I will do, first of all I will find the up to second derivative of y. So y1 is nothing but sine differentiation is cos m sine inverse of x. Now for sine, then now for the argument. For argument, what will happen? M sine inverse of x differentiation is nothing but root over 1 minus of x square. Is it? Okay, fine. Now I will multiply throughout by root over 1 minus of x square. So root over 1 minus of x square y1 is equal to m times cos m sine inverse of x, right? Now square it. So 1 minus x square y1 square is equal to m square cos square m sine inverse x. Now again differentiate it. So first function product rule, first function differentiation of second y1 y2 plus second function into differentiation of first minus 2x. Similarly in this side m square, so this power is there, so this power will reduce by 1 to m sine inverse of x, and for cos, so this for cos it is minus sine m sine inverse of x, right? Okay, so for cos square we have got this, for cos we have got this, then for m argument, so m divided by root over 1 minus of x square. Okay, so now if you notice here, this one is nothing but y, am I correct? So in fact this is minus y. So let me complete it. So 1 minus of x square 2y 1 y2 minus 2x y1 square is equal to minus 2 m cube, because m square and n will give you m cube, 2 is there, and then cos m sine inverse of x, and this is nothing but y into 1 by root over 1 minus of x square. Okay, here if I take this as equation 1, okay, now if this is equation 1, then look here, cos m sine inverse of x times m by root over 1 minus of x square is nothing but y1. So here I am getting that term, right? So I will write like this. So 1 minus x square 2 y1 y2 minus of 2 x y1 square minus 2 is there, m square I'll keep it out, so m times of cos m sin inverse of x divided by this root over 1 minus of x square is nothing but y1, so this gives me y1 into 1 y, right? Okay, so this is your this is what we need to prove, right? This is what we need to prove, and this is our, after simplification we have got this. So further we can simplify it. See, 2y1 2y1 2y1, I can throw out, I can cancel, right? So I'll be getting 1 minus of x square y2 minus y1 is equal to m square y, right? Now I will go for the Leibniz theorem. Okay, so here I will take this as u and this as v. Okay, and these are the single terms, so it is not required with the Leibniz theorem. So using Leibniz theorem, what I am getting, n plus 2, right? Because already 2 is there, so n times means n plus 2 into v. V is nothing but 1 minus of x square, right? Okay, plus nc1 u n minus of 1, right? So this will give you n plus of 1 because it will reduce by 1, so this will give you n plus 1 into differentiation of the v, first derivative of v, minus 2x plus nc2 yn and differentiation of this v1, differentiation of v1 will give you minus 2, right? So this is over. For this, Leibniz theorem is over, right? For this term we can simply, because this is only 1, so it is nothing but minus of y of n plus of 1 is equal to, this is negative here, minus m square yn, right? Now we will rearrange the terms. Okay, n plus of 2 now, okay, nc1 is nothing but n y n plus of 1 minus 2 nc2 is nothing but n into n minus of 1 divided by 2 into 1, okay, and yn minus of y n plus of 1 is equal to minus m square yn. Okay, so 1 minus x square yn plus of 2, now negative, this 2 get cancelled, yn plus of 1 I will take common. Okay, so negative of yn plus of 1 if I am taking common, and here it is yn plus of 1, right? So here 1x is remaining there, right? So 2y1 means this is x. Oh, so I have to go further for this, I have to go further, one more term will come here, let me change the color, sorry, so this is one more term will come here for this, so minus of un into v minus of nc1 is nothing but n, okay, un and v is nothing but 1, okay, so this is one more term it is coming here, so here I will have this minus x, and here we will have minus of n yn, okay, so n yn, okay, fine, so this x, now this x term is not there, for this term there is no x, okay, yn plus of 1, what I can do, I can take x out, x, and here also x is there, so I can write 2n inside the bracket plus 1 times x y n plus of 1, right? Okay, so this 1 2 3 terms gone. Here I am getting, if I take minus out, minus out, what I am getting? I am getting here inside the bracket n square minus of n. This minus I have taken out, so this will give you plus of n, and if this comes in the side, what I am getting plus, so it will give you minus of n square, okay, y whole y. So I am getting 1 minus of x square y n plus of 2 minus 2n plus of 1 times of x y n plus of 1. Okay, this and get cancelled, so if I take negative outside, so plus inside the bracket n square minus n square yn is equal to 0. So this is what we need to prove, right? Oh, thank you.